I'm naked, I'm numb, I'm stupid, I'm staying. And if Cupid's got a gun, then he's shooting.
This problem is a little bit different in terms that the charge carriers are not electrons but positive sodium ions instead. So we have an axon. It is a part of a nervous system. So it looks something like this. And there's a 35 millivolt potential difference from the outside to the inside. And there's some pumping action that tries to push these positive sodium ions outside or out of this axon cell against this voltage difference, and that requires some effort. It requires some power, and we are supposed to calculate how much power is needed. So effectively we are pushing charge carriers across a voltage, which means that we are pushing a current against the voltage. So we can evaluate this problem using our electric power solution methods. Power is voltage times the current. So we already know this voltage. The potential difference is 35 millivolts. Another question is, what is the current or amount of current that we are pushing through when we are pushing this much sodium ions through the membrane? So let's think about what this quantity means. So let's call it K. So it says that sodium ions move into the cell at a rate about 5 times 10 to the minus 7 moles per meter squared per second. So that many moles per unit area per unit time. 1 mole is 6.02 times 10 to the 23 particles, in this case sodium atoms. So this is, as you well know, the Avogadro's number. So if we multiply K by Na, we get how many sodium ions we are pushing per meter squared per second. So that's how many ions we have. If we multiply that number of atoms by their charge of 1 sodium ion, we know how much charge we are pushing through per meter squared per unit time. And if we multiply this amount by the area that we are pushing the sodium ions through, which is the surface area of the cylinder, then we get how much charge per second we are pushing, and that is the definition of current. Remember, current was amount of charge over a unit time, and this is what we have here. Just to be sure that this is really current, so let's check the units. So units of K are moles per meters squared per second, and Avogadro's number is 1 over mole. So we have 6 times 10 to the 23 particles per mole. So this is 1 over mole. Then the unit of charge is coulombs. The unit of area is square meters. So we get moles cancel. and the meters squared cancel, so we are left only with coulombs per second, which indeed is an ampere. Now we are ready to calculate the required power. So it's going to be the voltage times the current, so current comes from here. K times NA Q A I. Oh, that is I. And what is this? This is the surface area of this cylinder. So that's the diameter, and that is the length. So the area, surface area, is the perimeter, which is pi times d times the height L. So we get voltage times K times NA times Q times pi dL. And let's put in the numbers. Voltage was 35 millivolts, so 35 times 10 to the minus 3 volts. K, 5 times 10 to the minus 7 moles per meter squared per second. Avogadro's number, 6 times 10 to the 23, 1 over mole. Q are coulombs, so these are singly ionized ions, so their charge is same as the electron charge, but positive, so 1.6 times 10 to the minus 19 coulombs. Then we have pi, diameter 20 micrometers times 2 times 10 to the minus 5 meters, and the length is 10 centimeters times 0.1 meters. And that gives 1.07 times 10 to the minus 8 watts, which is about 1 times 10 to the minus 8 watts.